Hello to everyone and welcome to a new Energy Capital interview. My name is Anna and today I'm very happy to talk with Doug Robison, partner, co-founder, president, and executive chair of ExL Petroleum and chair of Abilene Christian University's Next Lab Oversight Committee. Doug will talk with us about the Next Research Alliance, which is an initiative to advance liquid-fueled molten salt reactors, mainly to address the world's need for clean, inexpensive, and safe energy, and as well for water and medical isotopes to treat cancer. Doug, it's great to see you today. How are you?
Thank you, Anna. Doing well. Nice to visit with you.
Thank you very much, Doug. Doing this interview with me is Aldo Santillan, Managing Director and Editor-in-Chief with the Energy Capital magazine. Hi, Aldo. How are you doing?
I'm good, Anna. Thank you very much. Very happy to be here with Doug today. I think he's going to share very interesting ideas with our audience.
That's right. So without further introduction, I'll start with our first question. Doug, why do you think nuclear could become the energy of the future? Could it replace hydrocarbons as the mainstay for energy?
The potential is there, and it's a matter of public policy. The future of hydrocarbons in our energy grid. I'm third generation oil and gas. I've had an oil and gas company for close to four decades now, and so I know the advances that have been made in that time period, as far as meeting the world's energy supplies that come from oil, natural gas, and coal. However, I also recognize that there is a push from a public policy standpoint, both in the U.S. and internationally, to decarbonize the grid, to move toward renewables. And as we do that, as we steward our current energy supply, we have to plan for the future energy supply. And nuclear is a proven technology that has been with us for decades, but has never been a mainstay in the energy market, I think primarily because it didn't need to be, because we got our power, our energy from hydrocarbons primarily. As we remove hydrocarbons off of the grid, and whatever pace that may happen is a matter of public policy, then we have to replace that energy supply with other energy. And that is where nuclear, and not just nuclear, but really advanced nuclear, comes into its own. And so what we've seen over the past, really I'd say the past decade, is the nuclear industry innovating in the area of energy. And so you have advanced nuclear, and even the project we're working on is considered to be fourth generation nuclear. And so it is, literally decades away in technology and what we normally think of nuclear energy. And so we see initiatives happening within the United States. They passed in 2018, 2019, bipartisan support, statutes that were signed into law under the previous administration supporting advanced nuclear. And so we see a renewing interest in advancing the role of nuclear as we, as a public policy, move toward decarbonation of the grid at whatever pace that's going to happen.
Doug, in this sense, why molten salt reactors or advanced nuclear reactors are safer and produce less weight than traditionals, and how can these reactors adjust to current levels of power demand?
So molten salt reactors are not theoretical or experimental. There was a molten salt reactor built in the 1960s here in the United States at one of the national laboratories. And at that time, we're going back to the 60s, nuclear was new. It was primarily driven by the Department of Defense. It was not driven by the need for energy, particularly for domestic energy consumption. But there was a molten salt reactor built in the 60s that operated for about 4 years. And then we moved to, as a country, we moved to light water reactors, which is what we're all familiar with for the most part. The key technology difference between a molten salt reactor and a light water reactor is a light water reactor has fuel rods that we're all familiar with, surrounded with water. That water serves as a coolant and as a heat transfer from the heat that is generated by the reactor itself. A containment dome that we're familiar with is to contain the eventuality that reactor overheats and that water phase changes into steam. And so you are containing that steam cloud. And water moves from a solid to a liquid to a gas in a very narrow temperature band. I mean, you can do that in your kitchen. You probably do it very easily going from ice to water to steam, right? And so that's really the physics involved in a light water reactor. And so the containment dome is to contain that steam cloud should that overheating occur. In a molten salt reactor, the fuel is not contained within a fuel rod, it's contained within the molten salt. So the molten salt is really performing several functions. One, it is performing the heat transfer function as you move heat from the reactor to a heat exchanger that you generate steam, and that's how you generate electricity. So the fuel is in the molten salt, but the molten salt is also the coolant. Now, the thing about salt is that you can, depending on the type of salt that you use, the melting temperature of salt can range widely. For example, we are currently building a salt loop with a melting temperature somewhere around 500 degrees Celsius. However, you cannot get salt hot enough to phase change into a gas. You can't turn salt into a steam, a salt steam, if you will, or a gas. What happens before that were to happen is the reactor, the metal itself would melt, or if you had a leak or an overheating in the event, then the salt doesn't change to gas, it actually refreezes into a solid. And so now you're not dealing with a steam cloud, you're dealing with a block of salt. And so under current technology, where you need that dome to contain the steam cloud, you need a ditch, figuratively speaking, to contain the salt, because the salt will refreeze back into a solid. So if you drop, for example, if your melting temperature is 500 degrees Celsius, as soon as you reach a temperature lower than 500 degrees Celsius, that salt and the fuel contained with it is going to be a solid, not a gas. And a gas goes into the environment, goes into the atmosphere. We saw that Fukushima, where you had a steam release of irradiated material, and you could register that all the way across the United States, which is very easy to measure isotopes or radioactivity. But we don't ever get into the atmosphere in a molten salt reactor, it turns into a solid.
So within the applications, Doug, how can molten salt reactors help address the global demand for fresh water and cancer diagnosis and treatments?
So the fresh water is just a function of heat. I mean, primarily nuclear reactors generate heat, and they generate a lot of heat. They're very incredibly dense from a power perspective, which is what makes them so efficient in generating power. So again, if you generate heat, then you turn water into steam, you turn steam, turns a turbine, and you have electricity. I mean, that's kind of the basic science, pretty well established and understood. Molten salt reactors do that, but they do it in a much more efficient manner. Whereas going back to current technology with the fuel rod, so you have a fuel contained within a fuel rod surrounded by a body of water. And you may have seen reactors in person. I've visited a number of university research reactors around the country, and you look down in the pool of water and you can see the reaction occurring below. The fuel rod, as that fuel generates energy, that fuel rod begins to decay, and you use 3, maybe 4% of the fuel contained within the rod before the rod has decayed to such a point that the fuel rod and the 97 to 96% of the fuel remaining in the rod is now waste. And so very inefficient. I mean, you're using 3 to 4% of the fuel. In a molten salt reactor, you use comparatively 100% of the fuel. You're not contained within a fuel rod, the fuel is within the salt. And so your efficiency from a fuel perspective goes through the roof in that you are using 99+% of the fuel to generate heat. Now that heat then can either generate power or electricity, as I talked about, or because it's high heat, it actually desalinates water, which is what you're questioning. And that's what's needed for desalinization. And so we're seeing interest in the United States and around the world. Half the world does not have drinking water. And one of the exciting things about this technology is you could take a molten salt reactor as a desalination plant, not as a power plant, although it could do both, and actually purify water because of the high heat process. Again, you're operating at very, very high temperatures, but you're also operating at very, very low pressures. And the threat, going back to a previous discussion, the threat from current nuclear is pressure, steam. I mean, you've all seen steam pressurized when you boil a pot of tea on the stove. You hear the steam. Well, that's pressure that you're hearing. The molten salt reactor doesn't have steam. It operates at low pressure and high temperature. And the high temperature is what fuels your efficiency, and it's also how you desalinate water. And then you asked about isotopes, I think, also. So the isotopes part of it is that at every nuclear fission incident, isotopes are created. It's a byproduct of the physics that happens. And so those isotopes are contained in two places, in the heart of the sun and at the bottom of a reactor. Well, in a fuel rod reactor, again, going back to the image of this fuel contained with the fuel rod that's sitting at the bottom of a pool, and that reaction is occurring down at the bottom of that pool, that coolant tank. Those isotopes are there, but you can't harvest them. They're at the bottom of the reactor contained within a fuel rod. And some of these isotopes have very, very short lives. A fuel rod, a molten salt reactor, you don't have the fuel rod. Your fuel is contained within salt, so you have a liquid system, right? You have a fluid system. So you're able, through chemical processes, to extract the isotopes directly from the fuel stream. And that's one of the exciting, to me, actually the most, if you were to say kind of a sci-fi aspect to this technology, is that a molten salt reactor has the potential to gather nuclear isotopes that are used for all sorts of cancer identification, prevention, treatments, and so forth. And the limited amount of research has been done. It's limited because it's so difficult to get some of these isotopes. Some of these alpha emitters, for example, it shows that it's a remarkable tool for the treatment of cancer. And so we're looking at this technology from a power standpoint. We're looking at this technology from a desalination of water standpoint. We're also looking at it from the perspective of advanced nuclear medical treatment. And that part of it is in some ways even more exciting. So the world needs energy. We need power for modern societies. We need water for drinking and cleaning, and we need isotopes. We need advanced cancer treatments. And these are things that touch really everybody's lives in one way or another.
Doug, what you have been sharing with us take us to talk about Next Research Alliance. So okay. Could you tell us more about it, please?
So the Next Research Alliance is an alliance of 4 universities. So you correctly introduced me as the executive chairman of ExL Petroleum. That's an oil and gas company. About 3 years ago, I began funding the advanced nuclear research that was occurring at Abilene Christian University, located in Abilene, Texas. Abilene Christian has a long history in their physics department, engineering department, of working with the Department of Energy. I saw the potential of this research, and it goes back quite a ways. In 2004, I helped write an energy plan for the state of Texas. I was appointed by Governor Perry at the time and co-chaired the Energy Supply Committee. And so we wrote an energy plan for Texas in 2004. Well, part of that energy plan for Texas was that we recognized that if we were to replace hydrocarbons on the grid, nuclear would be the technology we would have to primarily rely upon. So I had this in my mind from my work more than a decade before on where is the future of energy, long term. The Next Alliance, then that project catapulted rapidly from a research project through meetings with the Department of Energy here in the United States to where now we have a programmatic letter of support from the DOE, and they're saying you need to build this reactor. Well, then that became not a research exercise. That became how do we bring this technology? How do we commercialize it? How do we bring it to the world? So I formed Natura Resources, which is what this logo is. And Natura Resources is the for-profit entity that is funding the research now that we're talking about ultimately a commercial venture. Ultimately, the goal is to get reactors and isotopes and desalinization to the world. So Natura Resources, and that's Natura, has it's called Sponsored Research Agreement negotiated with Abilene Christian University, but also with Texas A&M University, the University of Texas, and Georgia Tech University. These four universities have worked together, and principally some of the researchers, the PhDs at the universities have worked together in collaboration for years. And so when we set out to tackle this problem of bringing the 1960s reactor into modern licensing efforts with the Nuclear Regulatory Commission, then all four universities form the NextRA Research Alliance. And so Natura Resources has sponsored research agreements negotiated with each of these four universities. We just finished a 2-day symposium here in Abilene with all the PhDs from the universities, comparing notes, looking at our research and how we're going to move this forward. And so it's a remarkable effort, combining four different universities of each that has incredible strengths. Two of the universities, actually University of Texas and Texas A&M, have on their campuses or nearby light water reactors. They have university research reactors, and so they have a lot of experience in Georgia Tech as well in operating and licensing of a research reactor such as we're currently working on. And so having their expertise involved is really remarkable. And within that team, then we have chemists, we have physicists, obviously of all shapes and sizes. We have engineers. We're now engaging biologists because of the medical aspects of this. And so we're pulling from all these universities all this brain power, if you will, and experience to help advance this research we're doing.
Particularly, Doug, what is the role of Abilene Christian University's NextLF in this consortium of universities and organizations, and what have been some of the results for ACU thus far?
Okay, Abilene Christian serves as, well, primarily Abilene Christian will be the licensee of the reactor. And so this is a university research reactor that we're working on. It's licensed through the Nuclear Regulatory Commission. Being a research reactor, it's going to be licensed to a university, and that university is going to be Abilene Christian University. And so Abilene Christian is the lead research team, if you will, in that they are going to be the host and the licensee of the actual reactor. And so there will be a facility constructed, and in the event that we get a construction permit, which is what we expect to do through the Nuclear Regulatory Commission, then we Abilene Christian with Natura funding will see to the construction of that reactor. And then we go back to the NRC for the operating permit, which is actually the permission to take the reactor critical. Then that reactor will be located on Abilene Christian in an Abilene Christian University facility. And then its primary purpose from that point is research. It's a research reactor. And so it's to conduct research and educate. So we have right now, we had an orientation a couple of days ago of 60 students from all over the world and all the four universities and multiple more disciplines than I could mention that are working this summer on this project. And so it not only is a research reactor, it's not only a tool that we are hoping to bring to the world, it's also an incredible educational tool. And so we have that research happening, that education happening at all four universities through the summer as well as through the school year. And that's one of the incredible kind of exciting aspects of this. The change that it's happened to Abilene Christian University is it has propelled, in a way, Abilene Christian University into the realm of sponsored research at a level that they have never experienced before, and they have risen to the task. So Abilene Christian has just hired Dr. Kruzalak, who is a vice president of research. And so Abilene Christian is stepping up to the plate as far as hosting this research, responding to the goals that we all have of advancing the technology and funding, for example, the facility that's going to house the reactor when it's approved by the NRC. In addition, Abilene is climbing the Carnegie scale of research institutions in the country. And so this, the scope of this research will propel them further up that classification of research universities. And then one of the other goals is to provide future research opportunities for ACU as well as University of Texas, Texas A&M, and Georgia Tech for their educational purposes, because their job is to educate the future leadership. And so part of what this provides, a big part of what this provides is a facility to do that. And so it's changing the face of Abilene Christian University in ways that are incredibly exciting. And, you know, I'm happy to be a part of that. I've actually sit on the ACU Board of Trustees, and so I get to put on my ACU hat fairly often and boast about what this is doing to ACU and how ACU is leading this research effort.
Doug, my last question will be about the role of Texas in advancing molten salt nuclear reactors research and development.
So Texas has always been an energy leader, I'd say domestically in the United States and also internationally. However, if you look at a map of where advanced research is happening, it is happening, and not just research, but I'll say advanced nuclear technology. It's happening primarily on the East Coast and the West Coast of the United States. Now, it's happening around the world as well, but I'm just talking about in the United States. However, Texas, if you look at the research project that we're involved in with the molten salt research reactor, the Nexter Consortium and the work that Natura is funding is anticipated to be the first nuclear license issued in the United States in close to 3 decades, and the first advanced nuclear license ever under the auspices of the Nuclear Regulatory Commission. And so we've seen Texas with 3 Texas universities, ACU, University of Texas, and Texas A&M, at the leading front of nuclear research. And so Texas has an opportunity, and I really have no doubt that Texas will seize the opportunity. I've been involved in the energy industry for close to 4 decades, of not only stewarding our current energy sources, and I include oil and gas and coal and renewables and all of that in that statement, but also looking to the future. And so we are working closely with the state of Texas, have met and will continue to meet with senior leadership in Texas and talk about how Texas can support this research and work hand in hand with the federal government, the Nuclear Regulatory Commission, and the Department of Energy, as we as a country and Texas as a state seeks to advance its own energy needs. And then, of course, we talk about the medical aspects and desalinization, which actually water is a big deal in Texas. Senate Bill 1 in Texas historically is a water bill. We're always dealing with water issues in Texas. And so desalinization is of great interest. And we have some of the leading cancer research hospitals in the world located in Texas. And so there's exciting possibilities of partnerships there as well. And we're starting to engage in those discussions and conversations as well. So I'm excited to see where we may go with the partnership in Texas. I look at this honestly as a series of partnerships, if you will. You know, we got Natura partnership partnering with these 4 universities, and we're partnering with the DOE and the NRC. And I say partnering, and that we're all trying to achieve a common goal. We seek the same kind of partnership not only at the federal level but at the state level, because it's going to take, I think, really going to take a group effort as we start to plan for the future of energy. Understanding we cannot have a gap in energy, right? We can't not meet energy demand because catastrophic things happen. It's like not feeding people. You have to have power. And so as the world is moving toward decarbonization, at whatever point that occurs, we have to have in place what's going to be next, right? And so my argument is that this technology, this research lies at the intersection of public policy and physics. Public policy is going to dictate to whatever level that we take certain actions, and specifically talking about decarbonizing the grid, decarbonizing our power. Physics then is going to dictate what technologies have the ability to fill that energy gap, right? And so that's the message to Texas. Texas is expected to grow by 25% over the next 10 years. We will have another 10 million Texans. I'm assuming those 10 million future Texans will all want to plug into the grid, will expect to have electricity. And so Texas has a challenge in front of it to meet its future grid demand.
Doc, thank you very much for sharing these insights and information regarding this very interesting project. And as you said, this will have very good benefits, not only on the energy side, but also on the public health side, if you wish. So I don't know, would you like to share some final thoughts with our audience in this regard?
Yeah, I'll be glad to. I think the main thing, as we constantly say, the main thing is to keep the main thing, right? So the main thing is, how do we get this technology into the world? You know, how do we help solve the world's energy needs, and how do we help developing underdeveloped countries become developed countries, right? They need power, they need electricity, people need water, and people have to deal with cancer. And so that is the motivation for getting this technology to the world. How do we do that? And it's there's not a pro-cancer lobby out there. So there's nobody arguing against the need to treat cancer, thank goodness. There's not a pro-dysentery lobby out there. And I don't think there's a lobby out there that says we don't need energy, right? And so it's, our challenge is, how do we respond quickly enough to the world's needs, understanding that we are dealing with technologies that have not really served these purposes, and particularly I'd say in energy has not been a primary source of energy, and yet physics and public policy may say this needs to be a primary source or a large part of our energy picture. How do we do that as a society? And that's where our partnership with the Nuclear Regulatory Commission, Department of Energy, the U.S. Congress and the state of Texas and others are going to determine how quickly we can advance this technology to bring it into the marketplace.